Science Setters, welcome to today's Grade 11 Physical Sciences show. Today we have a special revision lesson on chemical change.
Calculate deltaH for the following reaction. Is the reaction exothermic or endothermic? Okay, so what we're going to do is we need to go find. I need to calculate how much energy is taken in. So over here, okay, over here, that's my energy that's absorbed. Okay, and yes, I can write as well. Over here, that's energy released. Okay, so I need to work out total amount of energy absorbed, total amount of energy released, and I'm going to minus them from each other. Okay, now, do you know what I think, Abram?
Yes.
I'm going to get about halfway through this, and then we're going to need to take a break. So what I'm going to do, guys, is we're going to take a break, but while in the break, this is what I want you to do. I want you to decide for me what bonds and how many need to be broken, and what bonds and how many are going to be made, because that's a very important decision before we can actually move on. So let's just quickly get rid of my scribbles, and we're going to talk about what is actually happening. Now, the point here, grade 11s, is we need to be able to decide how much of everything we have. Okay, so we're going to start with the energy. Let me have a pen that works. Energy absorbed. Okay, so what we need to discuss is how many bonds need to be broken. So let's look at this carefully. What we have over here is we have a hydrogen fluoride bond. So it's HF, and there's two of them. The number in front is very, very important here, grade 11s. So we have two HF bonds. And now we go, well, we have a Cl2. We know that Cl bonds with Cl with single bonds. So we only have one chlorine-chlorine bond. Okay? Things like knowing that chlorine bonds to itself with single bonds is very important, grade 11s. It's those basic things that, even though we're not testing you specifically about bonding at this point, we still expect you to know it, okay? So you got to understand that everything gets put together. So let's go back to our table and see what we have there in terms of bond energy and that sort of thing. And hydrogen fluoride, HF, is 569. So I'm going to be using this one. And Cl is 243. Okay, I don't know these off my head, just so you know. I need to look them up. So let's go back here. Okay. Yes, there we go. All right. And we're back at the HF, and we said that was 569. And the chlorine was 243. Which gives us 382 kilojoules per mole. Okay, so we're okay with that. 1,382, not a problem. That means that I need to put in 1,382 kilojoules of energy per every mole of reactant in order to break everything up into its atoms. Okay, then the reaction proceeds. And now we need to look at energy released, because we're making new bonds. So we go back up and we say fine. Ooh, there we go. 2 HCl bonds, 1 fluorine bond, okay? So, no, the page, there we go. All right, 2 HCl bonds, okay, single bonds, we know that, plus 1 fluorine bond, okay? We go back to our table because this helps us decide what we've got, and we said, well, we've got 2 HCl bonds, so it's 431, 1 fluorine bond, which is 159. So we're going to go back, and obviously this is a little bit easier in an exam because you all have everything together, you know, and you don't have to swap through pages. So now we get 2 times 431 plus 159, and we get 1,059 321 kilojoules per mole. So, what is this information telling me, grade 11s? In order to break all the bonds, I needed 1,380 kilojoules of energy to go in. When the new bonds are made, I only give off 1,021 kilojoules. So actually, I'm taking in more than I'm giving off. That makes this endothermic. Okay, but now we need to prove it because they wanted us to actually prove it. So my change in energy, which is what they asked for, is going to be my total energy absorbed, okay, absorbed with a B, minus my total energy released. That little ZE thingy, funny symbol over there, that's sigma, okay? You know that from maths. Okay, so that means I'm going to go 1,382 minus 1,021, and I get 360 kilojoules per mole. Now, earlier today, I said to you that if delta H is greater than 0, then it is an endothermic reaction. This is very endothermic, okay? So this reaction, because delta H is greater than 0, it's an let me take that off. Delta H greater than 0, it's an endothermic reaction. Okay, it's endothermic. Question 1 says, and here it's about, and hopefully this will help with some of the questions we had with the positives and stuff, give the conjugate base for the following. So what I'm saying to you is I'm going to give you some acids, and I'm going to say to you, what is its base going to look like? It's an acid. We want to know what its base is going to look like. So that means I need to give away its hydrogen. So now we say to ourselves, okay, let's go down because I want to actually come. There we go. It's always important to talk to the board. Nitric acid, I can only give one hydrogen away. So it's an acid at the moment. It gives away its hydrogen. So that means, where's the undo? There we go. That means it becomes NO3 minus. It's only one minus because I only took away one positive. Okay, if I took away two positives, it would become 2 minus. So this is the acid. So here's my acid. This is my conjugate base. Okay, that's my conjugate base. So go to the next one, H2SO4. Now H2SO4 is quite special because it has the ability to give away 2 protons, okay? If it only gives away 1, which can happen, it's very unusual, but it can happen, we actually end up with HSO4 minus, okay? Why only minus 1 and not minus 2? Because we know sulfate's minus 2 because it only gave away one of its pluses. However, more likely is it's going to give away both its pluses, and it's going to become SO4 2 minus. That's its conjugate base. It's a very strong conjugate base. It's a weak conjugate base, sorry. It actually doesn't really want the hydrogens back. It's quite happy, okay? Now we've got another one, H3PO4. Now we've got 3. That means we actually can have 3 conjugate bases here because it's got 3 hydrogens to give away. So if it only gives away 1, it becomes H2PO4 minus. If it gives away 2, it becomes HPO4 2 minus. If it gives away 3, it becomes PO4 3 minus. Okay? Every time it gives away its hydrogen, it becomes more negative because it's giving away positives. Okay? In reality, when we react phosphoric acid with something, it's probably going to give away all 3 of its hydrogens and become pure 4,3 minus. So now we go, okay. First one we've got here is sodium hydroxide. And sodium hydroxide is going to gain an electron. This one's a little more difficult. Okay, so we have Na plus, OH minus. That's essentially what sodium hydroxide is made up of. And what will happen here is it's a base. It's going to act as an acid. Sorry, it's an acid. Let me start that again. It's a base which is going to take a hydrogen. A hydrogen is an H plus ion, okay? Which means if we look at the makeup of the sodium hydroxide, it's got to go to the OH. The sodium can't take it because the sodium is already positive, and positive won't go to positive. You know that. So it has to go to the negative, which means this becomes H2O. Okay? H2O here is now an acid. Sodium plus cannot act as an acid. Not a chance. An acid has to have a proton to donate. It has to have H plus ions. There are none in the Na plus, okay? So this is my base. This is its conjugate acid. Okay, it's conjugate acid. Please, this one's a little more difficult to see than with the acids. Potassium hydroxide, same thing. Potassium hydroxide is K plus ions and OH minus ions. So now we're going to say to ourselves again, we need to accept a proton, which means we need to accept an H plus ion. So we look at the makeup of the base and we go, not a chance. K plus cannot become KH. All right, does not exist as we've got it there. OH minus absolutely can take it. Forms water. H2O, that's its conjugate acid, okay? And I've said to you earlier today, of course, that water is an amphiolite. Here, it's making up its mind. Here it's going, I want to be an acid, okay? Because it is the conjugate of a base, okay? Next one, MgOH2, sorry. So if we go, let's look at it again. Well, that's Mg2 plus, even more positive than the last ones we looked at. And we have OH minus. I know there's 2 of them, but that actually doesn't make a difference here. And we've got to say to ourselves again, which of those are in a position to accept the hydrogen? Which of these are going to take the hydrogen, which would be the water, and then what is in the has the ability to give it away? Okay, so it's not the Mg2 plus. That is not an acid. Not a chance can that be an acid. All right, so be careful with your bases. Finding conjugate acids are far easier than finding conjugate bases from your acids are far easier than finding your conjugate acid from a base. Simply because often with the bases, it's going to create water. Okay, so be careful with that one. First thing we're going to do is we're going to say, okay, let's look at first identifying the acid and the base originally, and then we're going to find its conjugate. Okay, hydrochloric acid is an acid. We're happy with that. I'm just going to call it an A. We're going to make our life easier. Sodium hydroxide is a base. Oops, let me make it look like a B. Is a base. No one should hopefully be screaming at the TV just yet. Now I'm going to go, okay, what is actually happening here is the HCl is donating its proton to the NaOH, okay? So we're happy with that. On the other side, we've got to now go, all right, how do we recognize which is the acid, the base? And we go, okay, the HCl would have broken up. Remember, sodium hydroxide can be sodium chloride, sorry, can be NaCl, Na plus Cl minus, and water is H2O. If we look at the NaCl and we go, okay, for it to be a acid, we need to have a hydrogen present. There is no hydrogen in NaCl. It is so not an acid. It is definitely a base. It has Cl in it. That means it's paired with the HCl. Okay? Water, because it's now working with the NaCl, it's definitely in a position to give away a hydrogen. It's become an acid. So it is the sodium hydroxide's conjugate acid, which we've actually just done. We just looked at the conjugate base acid to sodium hydroxide. Let's look at H2SO4 and KOH. Well, the H2SO4 will give its hydrogen to the potassium hydroxide. So sulfuric acid is the acid, potassium hydroxide is the base. And we go, well, all right, we've just done this, that we know that potassium hydroxide's conjugate acid is water. So they will go together, which then means that sulfuric acid's conjugate base is the potassium sulfate. Okay? The potassium sulfate is in a position to accept hydrogens if the potassium goes away. Okay? Which means if it can accept hydrogen, H plus ions, it is a base. Last one, and I'm hoping by now you guys are starting to see the trend. Let's just take it so I've got a little bit more space. Okay? And let's change color. So sodium hydroxide, that's a base. Nitric acid is an acid. We just did sodium hydroxide. And we go, no, we know this. We know that for the base, because it takes a hydrogen, remember it's going to take the hydrogen from the from the nitric acid. That's going to give me water. Water here is going to be an acid. Okay. We're going to take that away. It's really just not playing ball with me, so it's going to be an acid. So sodium hydroxide's conjugate acid is water, which means nitric acid's conjugate base is sodium nitrate. Please, these questions have been put the way they are because I do not want you to learn that first goes with first, second goes with second. Okay? Because that's what happened in the first two. First one on the left, first one on the right, second one on the left, second one on the right. Please don't learn that. Okay? Because we don't have to write it in that order. And you can see here that's not what happened. Okay? So please don't learn that. It's very, very important.
Okay, guys, I hope you are enjoying this revision session. If you are struggling and need help, remember to post on the Facebook page facebook.com/learnextra. Now it's time for a break, so don't go away. We'll be right back. Welcome back, guys. I hope you are getting into the idea of revision. Please let us know how you are doing. I'd love to chat to you on Facebook and on Twitter. Enough of the chat. Let's get back to revision.
Starting with, what is a strong and a weak acid? Now, what's really important here is we define a strong acid, an acid which ionizes almost completely. Now, I've deliberately gone and bolded and underlined ionize because you've got to remember that all your acids are covalently bonded molecules, grade 11s. So that means they're not naturally ionic. So they haven't given away electrons, they haven't taken electrons, they're sharing them. So what happens is when the acid dissolves in water, we have to force it to become ions, and that's really, really important. With a strong acid, it desperately wants to become ions. So when we look at a strong acid like hydrochloric acid, when it reacts with water, and what's very important here is that we say it is reacting with the water, it's part of the reaction, okay? We end up with H3O plus ions because what's happened is the chlorine, the hydrochloric acid, has given its hydrogen away. It's acted like an acid. Remember, acids are proton donors. We did that last week. The water acts like a base, takes the hydrogen, ends up with H2O plus and Cl minus. Now, this is a strong acid, so that means when I look at this, if I could look at this solution from in a microscope and I could actually see the little molecules everywhere, there would be lots of H2O plus and Cl minus. And remember, I said to you last week as well that it's this H3O plus that makes it so dangerous, okay? It's the H3O plus ion that corrodes, that eats away skin and metal and all those wonderful nasty things. Moving on. So, when we look at a weak acid, and it's hard to see it from the equation because of the way we write the equation at this level. When you get to grade 12, you're going to do a thing called chemical equilibrium, and you're going to do the whole thing with reversible reactions, which you've seen. And this is, we're going to rewrite these equations with the sign doing this. Little sign to the right, sorry, big sign to the right, little sign to the left. And that tells me that I have lots and lots of ions in there. With my weak acid, like acetic acid or ethanoic acid, vinegar, okay? Remember, it's only that little hydrogen at the end that's important. The one that's bonded to the carbon isn't important, okay? It doesn't make it acidic. That hydrogen comes along, donates itself to the water, okay? Off it goes. Once again, we get H3O plus ions, and now we get the CH3COOH minus, okay? This is a weak acid though, so what that means is that when this dissolves in the water, we get it to ionize, but we don't get a lot of product. There's very little of this. So because there's so little H3O plus, it's not very dangerous. Doesn't mean that it can't do damage, okay? So what I'm saying to you is don't go and drink a whole bottle of vinegar. You are going to feel fairly sick after that if you can actually get it done. Okay, so you got to be careful because remember your stomach's got acid in it. You don't want to add to that, okay? But lucky for us, vinegar, if you spill it on your table at home, isn't going to eat through your table, okay? Which is a good thing. So acids ionize, very, very important. A base, before we get there, now I've got a list here. And this, of course, is in the notes you can download. Please, grade 11s, you have to just learn this. This isn't something where I can say to you, look at the structure, look at how many hydrogens there are, because it doesn't work like that, okay? And these are your common acids. So these are the acids you're most likely to find at school. These are the ones we're going to deal with calculations, with experiments, all of that sort of stuff. And they expect you to know whether they're strong or weak, particularly for next year, because next year we're going to look at titration in a lot more detail than we're doing this year. And in fact, you're going to have to calculate final pHs. It's going to get all nice and hairy for you guys. It's great fun. And from knowing whether you have a strong acid and a strong base, you have to choose what indicator you're going to use. So that's really, really important. And unfortunately, this is one of those things you just have to learn, okay? I know, I mean, I still get confused at times, but I know them because we use them all the time. First four, hydrochloric, nitric, sulfuric, phosphoric, these are all strong acids. Phosphoric isn't that strong, but it's still classified as a strong acid. Then we get carbonic, and remember I told you last time, carbonic acid is what you find in your fizzy cold drinks. In fact, you find a little bit of phosphoric acid too, okay? And carbonic acid's the one that they reckon will rot your teeth, and you can use to marinate meat, and all those fun things, okay? Ethanoic acid, which, you know, is vinegar, and then oxalic acid. This one's quite an unusual one. Don't stress at this point about its structure and the fact that it's COOH in brackets. You're going to deal with it when you do organic, okay? The nice thing about these two is you're going to remember how to name them and draw them when you do organic chemistry next year, which is actually going to be a lot of fun. Okay, so that brings us to bases. Now, a base dissociates. There's only one exception to that, and I'll talk about that in a second. Bases dissociate because bases are ionic. Bases are made up of your negative ion, which is usually OH, but it doesn't have to be. It can be nitrogen, it can be carbonates, it can be oxygen. So it's a negative ion with a metal, generally speaking, except ammonia. Ammonia is your exception to this whole thing. So ammonia is the only base you have that's covalent. Most of your other bases are ionic. Now what that means is when they get added to water, they split apart. They dissociate from each other. Much like water's like that third wheel. You know what I mean? You have a friend and you're best friends, and then water happens. Generally it's a boy, okay, if it's two girls, and then you decide you don't want to have anything to do with each other anymore, okay, because, you know, water got in the way. And if you don't, you know, sometimes that dissociation is fairly permanent, and sometimes you actually manage to get over it and, you know, kick the boy out and you become friends again. All right, but what does that mean? Water doesn't actually take part in the reaction. So look at the difference in the way we write this. Here I have sodium hydroxide. The water gets put on the top. It gets put in the arrow because it's not part of the products. And literally, I'm splitting the sodium hydroxide in half. So I'm breaking it up into its ions, Na plus, OH minus, okay? I could write it with the water in the middle. So then I'm going to get the fact that water's starting to act like a acid in this case, but that gets quite complicated with what we're trying to do, okay? But it's a strong base. NaOH is a very, very, very strong base. It's caustic soda. It is extremely dangerous, okay? It's not one of those things you should have in your home, and if you do, I'm a little worried. And it's one of those things that we use as industrial cleaners, very, very dangerous. Can burn you, and this is one of my pet peeves, it can burn you as badly as an acid can, okay? And in fact, when you mix sodium hydroxide into a solution, if you're not careful, it can bubble up so much that if it gets in your eye, it can blind you. It's very, very dangerous, okay? And Looney, remember last week we spoke about that episode of the program? It's actually CSI.
Yes, yes.
And the guy falls into the pool. And
yeah.
It's not pretty. And it's only with organic material. Sodium hydroxide loves organic material, okay? So I'd be fairly safe in my clothes because I think most of it's synthetic, so we'd be fine. Okay. Your weak bases, something like your carbonates, generally carbonates are weak bases, also dissociate, breaks where the metal is, breaks up into two, okay? What's important here is you've got to remember what your polyatomic ions look like, what their charge is, and all of that sort of thing. Now, there's an exception, grade 11, so I want you to just pay attention to this, and that's ammonia. Ammonia is actually a weak base. We use it at home a lot. It's a very good cleaning agent. You smell it in Handy Andy and all of those sort of products, so they are moving away from it because it's toxic, not because it's a base, but just because it is toxic, just in the format that it is. And ammonia has that very pungent, it feels like it's burning your nose and your eyes, and it's just not pretty. And in fact, you get Fibs ammonia, which is only, I think, 33% dilution. But if you don't wear gloves, when you use this, it actually burns the first layer of your skin, and your skin feels like leather and it peels. And yes, I'm talking from experience, but we'll move on. Okay, always read the instructions. I'm just saying. Yeah, I was young. Okay,
at least you went like now.
Oh no, I learned my lesson the first time. Anyway, now with ammonia is going to have to ionize. Okay, ammonia is not ionic. It's two nonmetals, which means the water is going to act like an acid, give its hydrogen to the ammonia, and it's going to give us the ammonium ion. So that should be plus, and that's minus. Now, you've seen this before, grade 11s. Beginning of the year, you did covalent bonding, and you did dative covalent bonding. This was one of the ones you had to learn to do. So there's lots of stuff involved in the ammonia, okay? And remember, this is my base. This is its conjugate acid. Ammonia is your exception to dissociation. It ionizes. I'm going to start with the fact that an acid plus a metal gives us salt plus hydrogen. And I really am hoping you've seen all of these. Okay, unfortunately, we don't have time to do them, but I really am hoping you have. But if we look at the first one, it's an acid plus a metal. So let's keep them nice and simple. So if we go hydrochloric acid plus, let's make it magnesium. Okay, it's going to give me a salt plus hydrogen. The hydrogen part's easy. Okay, now to work out the salt, what happens here is we go, well, the acid's going to split in half. I've already used the hydrogen because I made the H2. So the chlorine's going to bond with the magnesium, okay? Chlorine's going to bond with magnesium, which means I'm going to make magnesium chloride. And here's where being able to write formulas is very important because we recognize that it's MgCl2. And of course, we can't leave it looking like that because your teachers will be very unimpressed with you. So let's write it properly. That would be HCl, and it would need to be a 2 in front of it. Grade 11s, as this must become second nature. So maybe when you write a test or exam, make a big note for yourself on the top of your paper and go balance chemical equations, okay? Make sure you always balance chemical equations. That's very, very, very important. So that one's not so bad. The next one, acid plus a metal oxide, okay? Let's take sulfuric acid. Let's be a little bit different, okay? And we need a metal oxide, so we've already used magnesium. Let's use sodium oxide, okay? It's a little more difficult, so sodium oxide would be Na2O. And now we go, okay, gives me a salt plus water, which means I know the N's going to be plus water. The salt comes from the fact that the hydrogen and the oxygen make the water. Makes sense, hopefully. And this is a swapping partner thing, okay? The plus hydrogen plus oxygen minus go together, which means the sulfate, which is minus, goes with a positive Na. Once again, make sure you can write formulae, but this becomes Na2SO4, and that's already balanced. So that one wasn't so bad. That's actually quite a nice one, okay? Then we have, and this is the one you're going to see often, acid plus a metal hydroxide. Okay, so let's take HCl again, and this is the one you're going to see most often. HCl and sodium hydroxide, NaOH. Hopefully you know this. The nice thing about this reaction is that it gives us a salt, otherwise known as table salt, NaCl, okay, plus water. Grade 11s. And I've had this discussion with my learners recently. You really struggle with the concept that we call some of these salts, okay, simply because you're so used to, you know, you go out for dinner or you're at the dinner table and you say, pass the salt, okay? What do you mean by pass the salt? You mean pass the sodium chloride, okay? Sodium chloride's common name is table salt, actually, okay? But we just shorten it to salt. Could you imagine every time you went out for dinner and went, please pass me the table salt, or pass me the sodium chloride? I think people are going to start looking at you funny. And
Yeah,
really?
they
Maybe I
will.
should start trying that. No.
Pass me the sodium chloride, please.
Yeah, I'm going to get some funny looks. All right. But what that means is in your head, and I can understand it, is you go, salt must be sodium chloride. No, 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 no. A salt is the name given to an ionic compound, okay, with a metal and a non-metal. They are salts, okay? When the ionic compound comes together, it is a salt, okay? So keep that in the back of your mind. Now the more difficult one. Acid plus a metal carbonate. Now, carbonates are your weak bases, okay? So let's take HCl, let's not make this too difficult, and add it to sodium carbonate. Na2CO3, okay? Now, the reaction says to me, I'm going to get salt, which hopefully you guys are screaming at the TV going, no, I know what it's going to be. Sodium chloride, absolutely, NaCl, plus water, H2O, plus carbon dioxide, CO2. And to balance it, I need a 2 in front of here. Where does the CO2 come from? It comes from the CO3, okay? The CO3 gives me the CO2. The one oxygen from here also ends up with the water, and so it splits up, okay? So if you ever a little confused as to whether I'm going to get carbon dioxide, you must have the carbonate in it, okay?
Now it's time for a break, so don't go away. We'll be right back. Welcome back from the break. I can't believe that spring is here, and soon it will be time to plan for your final exams. Don't stress, exam school is coming in term 4. We'll be here to support you all the way. But for now, let's get back to today's revision lesson.
So let's read it together. Good technique whenever you are given an exam question, get your pencil, get your pen, and see if you can identify things as we read through them. So it says HCl. Now I know that that means that's hydrochloric acid. So I'm just going to write there acid, and I remember it's hydrochloric acid. And NaOH, that's sodium hydroxide. And this is a base, but it's a soluble base. And remember, a soluble base, another word for a soluble base is an alkali. Okay. So they react together according to the following balanced equation. Now guys, even if they say to you it's a balanced equation, make sure that you check that it is balanced. So I'm going to quickly check it. I say one hydrogen here and another, that's two hydrogens, and I've got two hydrogens there. One chlorine, I'm happy with that. One sodium, one oxygen is balanced. During a titration, 6,5 centimeters cubed of dilute hydrochloric acid neutralizes exactly 25 centimeters cubed of sodium hydroxide solution. If the concentration of the HCl solution is 0.2 moles per decimeter cube, calculate the concentration of the sodium hydroxide. An acid and a base reacting together according to the following during a titration. Now a titration is simply a chemical process where you take a drop at a time. You've got your base and you add to it your acid. In this case, it says during a titration, 6,5 centimeters cubed of dilute neutralized exactly 25 centimeters cubed of the base. So you have 25 centimeters cubed of the base of the alkali. So usually it's in a flask like this, and there's our 25 centimeters cubed, 25 mils of your sodium hydroxide. And what happens is that what we're going to do is we're going to take one drop of acid and we add it to it. And then we take another drop and we add it to it. And usually you have an indicator in here as well. And when you choose your indicator, so that exactly when they're exactly the right number of drops of acid and bases to neutralize each other, so that you don't have any more reactants. Remember, these things over here are called reactants. When all of these are gone, so they don't exist anymore, they've combined, and you've only got that, that's the point that we say completely neutralized. Completely neutralized. It means that there's not even one little sodium hydroxide or hydroxide molecule or ion floating around. So what we're going to say is we're going to say that, look, if we take sodium hydroxide and we take hydrochloric acid, what's going to happen is we want one of those to match up with one of those, and that's going to form HOH. And what's HOH? Any idea? HOH? Well, look, it's another way of writing H2O, which is water. So we know water is neutral. It is the pH equal to 7, and it is neutral. Okay? So what we're looking at is here, in a base or an alkali, we have lots of these. There's a high concentration of those, high concentration. In the acid, there's a high concentration of these. And when we combine them, we want to make sure that they match each other out, so that they join together. And look what else is left over. We've got that thing, and we've got that thing. That one will be, this one is positive, this one is negative. They join together and we form sodium chloride. So I hope you can see in a titration, it's really a balancing act. It's about getting the right number of things to join together. Now, I hope you've got it and understand that even though you've got sodium hydroxide and you've got hydrochloric acid, hydrochloric acid is a strong acid, sodium hydroxide is a strong alkali, so it will form its ions. but we need to have the right number. They don't have to be of the same concentration. We need to make sure in this solution of water that we've got the same number so that they all match off. And that's the calculation we're going to do. So let's just get that clear. And I hope that's answered the question about titration. So during the titration, we've got the volume of the acid, because it was dilute acid. So I'm going to write down here, volume of acid. Just let me, volume of acid was equal to 6,5 centimeters cubed. My volume of base, and I'm just going to call it base even though it's alkali, was 25 centimeters cubed, and it was exactly, that was the exact neutralization. The other thing that we are told is we're told the concentration of the concentration of the acid is 0.2 mole per decimeter cubed. So we know the concentration of the acid of HCl is going to be equal to 0.2 mole per decimeter cubed. Just want to check that I've written that down correctly. I think I have 0.2. I don't want to make a mistake. Okay, so guys, what we've got to make sure of is that we partner up the acid and the base together so that we've got the same number that they neutralize. How are we going to do it? I want to give you a foolproof method, a safe method. Now, you might read in your textbook that you've got this funny equation with a ratio and Na and Nb. And guys, I don't buy that. Take it slowly, work it out step for step, and you will never go wrong. In the first place that I start, don't make any tricks. I write the balanced equation. So I'm going to say the balanced equation, HCl plus NaOH, to give me NaCl plus H2O. And what I'm going to recognize is that from the balanced equation, that one molecule of that, or 1 mole of that, will react with 1 mole of that to produce 1 mole to produce 1 mole. This isn't always the same. What it's saying is that in this case, they're in the same ratio. 1 is to 1 is to 1. So that means that if I've used up 1 mole of acid, then I must neutralize that with 1 mole of base. And I will produce 1 mole of salt and 1 mole of water. So the question now, guys, is how many moles of acid have I got at the beginning? Well, how do I work out moles? And that's the critical thing. If I've got concentration over there, and I've got volume, I can work out concentration. And that's exactly what I'm going to do. So let's go and try it. I'm going to just leave that up there for the moment. I'm going to remind you that concentration is the number of moles divided by the volume. And we're wanting to work out the number of moles of acid. So I'm going to substitute in, first of all, I'm going to say 0.2 is equal to, I don't know the number of moles, and the volume here, what was the volume given? It was given as 6.5 centimeters cubed. Hey, I can't work with centimeters cubed. What is the SI unit for volume? It's not centimeters cubed, it's decimeters cubed in this case. Because concentration is given as mole per decimeter cubed. Now you need to remember that a centimeter cubed is like a milliliter, and a liter is like a decimeter. So how many milliliters in a liter? Well, there are 1,000. How many centimeters cubed in a decimeter cubed? 1,000. So we divide by 1,000, and when I divide by 1,000, I'm going to just simply say that's 6.5 times 10 to the minus 3 decimeters cubed. Don't forget to change your units. And we'll put that in, and we're going to say it's 6.5 times 10 to the minus 3, and now we've got to solve for n. So, guys, I'm setting it out, wrote the equation down, substituted in the value, and now I'm rearranging. The reason for that is I've now got my marks for substitution and my marks for the formula. If I happen to make a silly mistake, I will still get my marks. Now, this is the moles of acid, and I'm going to say the moles of acid is equal to 0,2 times 6,5 times 10 to the minus 3. So, let's call out the calculator, because I'm not going to trust myself to do that in my head. I'm going to say 0,2 times 6,5 exponent minus 3 equals, and change it, and it gives me 1,3 times 10 to the minus 3. 1,3 times 10 to the minus 3. 1,3 times 10 to the minus 3 moles. Okay? I'm not worried about changing it back into a fraction. I can work in in scientific notation. But what does that tell me? Guys, you've got to recognize this. That if I've got 1,3 times 10 to the minus 3 of those in moles, so there's my number of moles. If I've got that moles, then I'm going to have how many of these? I've got to have the same. It's 1 to 1. 1,3 times 10 to the minus 3. I've got to use that. That's my number of moles. So if I know that's my number of moles, remember the original question was, can you calculate the concentration of sodium hydroxide? And we now know the number of moles, and we know the volume. I'm just going to change the volume here to 25 times 10 to the minus 3. And let's now calculate the concentration. So I'm going to use exactly the same little formula, but I'm going to change it this way around. I'm going to say my concentration of sodium hydroxide is equal to the number of moles divided by the volume, which in this case is 1,3 times 10 to the minus 3 divided by 25 times 10 to the minus 3. Okay, so let's put it on the calculator now, and let's see where we go with that. So there's my answer, and I want to divide that answer by 25 exponent minus 3. And I get an answer of 0,052. 0,052. Right, let's write that down. So we're going to say the concentration is 0,052. Don't forget the units, mole per decimeter cubed. Excellent. Here's a question. We're not going to have time to do it because it's so similar to the previous one, so I'm going to skip it. But here's a word that I want to just explain. Ethanoic acid. So ethanoic acid is an organic acid. Okay, it has a formula of CH3, COOH, so CH3, COOH. That is also called acetic acid, and to the slub chips brigade, it's called vinegar. Okay, so if you are told to go and get some ethanoic acid to have with your supper tonight, then go and get the vinegar. Okay. I'm going to leave this one. Yeah. I tell you what, that one is in the notes, and we'll post the answer at the end of the lesson, and make sure that you can check it out for yourself. But question 3 is rather interesting. So I want to get to it because we're running out of time. So let's go over here, and let's make sure that we are on track. So I don't know how much of question 3 we're going to do, but I'm going to try and go a little quicker than I was, but still make sure you follow me. So it first of all says, what mass, so they're asking for mass, what mass of sodium hydroxide is needed to prepare a 200 centimeter cubed solution with a concentration of 0,4 mole per decimeter cubed. Guys, this is a question that is often asked in the exam, can even be asked in a practical exam, because a solution that is of a known concentration, with a known concentration, is called a standard solution. Standard solution. So we want to know what mass is going to dissolve in 200 centimeters cubed to give us a concentration of 0.4 mole per decimeter cubed. So what have we got? We know concentration is the number of moles over the volume, but we also know that number of moles is equal to the mass over the molar mass. So we don't know the number of moles that we need. We want to find the mass, we want to find the number of moles, and then we want to find to get the right concentration. When you make a standard solution, you've got to measure out accurately the mass of substance, and then add a little bit of water at a time, dissolve all the solute. Remember, the substance that is being dissolved, the solid stuff, is called the solute. The water that you're adding is called the solvent, and you dissolve it in a volumetric flask, so everything dissolves, and then you add slowly, slowly, slowly until you get to the line on the volumetric flask, which will be exactly the 200 centimeters cubed. Okay, so that's the process. The calculation is a combination of these two equations. Now, what I've learned is that you can combine these, and you can do it by simple substitution, and you can find that mass is equal to concentration times the volume times the molar mass. Check it out and make sure that I've got it right. You'll see over here that if we take this one and we rewrite it for number of moles, we substitute it over there, you will see that you can get that equation. So mass is equal to concentration times volume times molar mass. We want to find the mass. So what have we got to substitute in? Simply got to substitute in the required concentration. The required concentration, 0.4. What was the volume we required? Now, hey, they try to trick us. Centimeters cubed again. We want not 200, but we want to divide the 200 by 1,000. So if we divide it by 1,000, it's going to be 0.2. So I'm going to take 0.4 concentration times 0.2. Now times the molar mass. Hey, where do I get the molar mass from? Well, guys, you need to remember from your stoichiometry and your section on moles that you look on the periodic table. So if I go to the periodic table here, I'm wanting the molar mass of sodium hydroxide. Sodium is 23, oxygen is 16, and hydrogen is 1. So if I add those two together, look at the periodic table, and I can get that the molar mass of sodium hydroxide turns out to be equal to 23 plus 16 plus 1. Now, on your periodic table, there might be 2 decimal places. Please include them. I'm just doing it on this older periodic table that was rounded off. But I also remember that the molar mass of sodium hydroxide is very close to 40 grams per mole. So I'm going to substitute that in there, the 40 from that. And if I multiply this out, see what I get. I'm going to say, right, let's move it across. I'm going to say 0.4 multiplied by 0.2 multiplied by 40. And it tells me I need exactly 3.2 grams of sodium hydroxide. 3.2 grams 3.2 grams of sodium hydroxide. Okay, so there we've got the first part of the question done.
We've come to the end of today's show. Thanks for joining us and for chatting to me during the show. Remember to visit our website, learnextra.co.za/live to get the notes and to watch the videos from the term. If you are stuck on any questions, make sure you post them on Helpdesk at learnextra.co.za/helpdesk. From all of us at Learn Extra, have a great September holiday and join us again from the 30th of September for Term 4.